Alright, it's quicker for me to upload if I keep these parts shorter than 15 minutes, so hopefully the first part wasn't too long. Alright, with these I want to recognize that I can move all of these back to become exponents. I can't use the rule of logs until these coefficients are gone. So log to the base b of x to the minus 4 plus log to the base b of y to the minus 3 plus log to the base b of z to the 1/5. Now, thinking backwards to the one we just did, we're going to combine two logs that are added. We're going to take their arguments and multiply them and make it one log. Then this plus sign here, we're going to add, since it's added, we're going to multiply its argument as well. Alright, it'll be a little clean, we're going to clean it up a little. Let's just put the x to the minus 4 on the bottom and the y to the minus 3 on the bottom, and it all looks nice and neat. And that, notice we start with an expression with 3 logs and we end it up with 1. We condensed it using the rules of logarithms. On number 12, we are going to solve for x. And this is an equation where the unknown is in the exponent. So we're going to call this an exponential equation. Alright, the first step is to get the term with the exponent by itself. So I'm going to divide both sides by 7. And I get 10 to the x minus 3 equals 12 divided by 7, which is 1.7143. Now I need to get that exponent down where I can solve for it, and I do that with the word log. Because this is base 10, I'm going to use log because log is base 10. So I'll write it in there for emphasis. What exponent do I get raised 10 to get 10 to the x minus 3? X minus 3. And log of 1.7143 is 0.2341. And we finish up by adding a 3 to both sides. So the 3 pops over here. Since I ran out of paper, I will just go like that. So the final answer is 3.2341. If you plug that back in the original, it should give, if you put that number in here, you should get a 12 or something very, very close. Alright, the last one for tonight. We're going to use we're going to use logarithms in some steps of this problem. Suppose we have a radioactive element which has a half-life of 15.2 years. What that means is in 15.2 years, whatever you started with is now in half. So half of it has disappeared in its radioactive decay. So let's say we started with 52 grams of this element, and how many will remain after 50 years? This is a pretty typical problem, and you'll see that logarithms will allow us to do it. You'll recall that the basic form that we use to answer this question is this formula, which has to do with exponential growth and decay. When we have that, you see there is a k, and that the strategy is find k, use k. So on this side, we're going to find K with the fact that the half-life is 15.2, and we start with 52 grams, 15.2 and 52. So the amount in 15.2 years is half of 52. So I don't know what 52 is. 52 divided by 2 is, but I could get that. What is it? 26? I think it is. So 52 divided by 2, that's what we're going to have. We start it with 52. E, we don't know what K is, but we know it's going to take 15.2 years for this decay, to go from 52 down to 26. So this is a 26. So now we divide both sides by 52. That'll always give us a 0.5 on this side, equals e to the 15.2k. We want to find k, it's up in the exponent, so we're going to take the ln of both sides because there's an e here. So there's an unwritten base e here. ln of 0.5 equals, I guess I didn't write that down, but I end up with ln of 0.5 equals, what exponent do I give e to get e to the 15.2k? 15.2k. So I did write down what I got when I divide ln of 0.5 by 15.2. That'll give me a k. It should be negative because this substance is disappearing. And small negative number. Found k, use k. Alright, so we're going to go back, start again. Now that we have k from this information, we're going to answer how much after 50 years. So we want the amount in 50 years equals the amount at time 0, which is still 52. E, we know k because it's negative 0.0456. And times t, that's our 50. Sorry, run out of room there. Let me write it down here where it's a little more clear, more space. So we have a sub t equals a sub o e to the k, which we know now. We're looking for the amount in 50 years. And the amount when we started was 52. E to the k, which was negative 0.0456 times years, 50. So this is just tap it out, and we get, once we put this in our calculator, we'll get, there's only 5.32 grams left after 50 years. Alright, that took us through some of our logarithmic and graphing and difference quotient skills. So I hope you were able to keep up with that and come ready to do these exact type of problems tomorrow. All right, carry on.